Good morning, everyone. I hope you're doing well. Happy Friday. I'm going to go ahead and get straight into the notes. Okay, so today is day 2 of notes for Unit 1, and we're going to be looking first at physical separation methods. How do we separate mixtures? Because we know that we can separate them by physical means. We don't have to have some fancy chemical reaction to separate Kool-Aid, or at least the Kool-Aid powder from water after it's mixed. Once you mix the Kool-Aid together, we can figure out a way to separate that mixture. Let's talk about it. Okay, these techniques work because different parts of a mixture, I'm going to continue to use Kool-Aid as my example. That Kool-Aid powder and water have different properties. They're not made of the same type of atoms, so they have different properties. So we can separate them by exploiting the differences in their properties. That Kool-Aid powder has a different density than water. The Kool-Aid powder has a different boiling point than the water. The Kool-Aid powder has a different density than the water. So we can separate it by exploiting those differences. Okay, distillation. Distillation, we're on it. So distillation is the separation of a mixture by the difference in boiling temperatures. This is how they make alcohol. So like Germex, if you can, there you go. So the process in order to make Germex, which a lot of distillers that normally make alcohol have been able to switch to making Germex because it has to kind of go through a similar process. They just tweak a couple things, and instead of making vodka or rum, they make Germex. Okay? And it's about boiling the different components in a mixture to the point where one burns off and the other one hasn't quite reached that boiling point and it's left behind. Okay, filtration. Filtration is separation. Filtration is separation by particle size. Okay, and all of y'all do this in the kitchen whenever the noodles are done being cooked. You get a strainer out or a colander, and the holes in the colander or the strainer are small enough so that the water will pass through from the pot, but not any of the noodles will get through. And that's just all filtration is. Also, if you have like a life straw where you're sitting there and you're sucking out all the water, but you know you're getting filtered clean drinking water. Flotation and decanting. Did you know that the way that they harvest cranberries, have you ever seen the Ocean Spray commercials where they're standing in the waders about chest deep in the water and they got a bunch of cranberries floating on top? Well, cranberries are hollow in the middle and have like a little air pocket, so they're not very dense. They have low density, so they float whenever they're exposed to water, which means, sorry, I'm just getting a little bit more Germex coughed into my hand, which means the way the farmers actually harvest cranberries is they have their John Deere tractor with this attachment that basically ruffles up all of the cranberry bushes, I guess is the correct term, and loosens all the berries, and then they flood the field. The berries float to the top, and then they have a harvester that comes by and just right off the top and makes it to where harvesting the cranberries is a little bit easier rather than individually plucking each cranberry. Okay, so it's a difference in density. And then decanting is what people do whenever they, whenever you're trying to, what is it called? Panning for gold. That's what it is. because gold is super dense, super heavy. If you ever hold like a little nugget of gold, it's really, really, really dense and heavy. So it's always going to sink to the bottom, just like you can see in this picture, how you have like that soil or that sediment or rock or whatever at the bottom here. It's going to settle at the bottom and let the less dense water flow out first. Okay, chromatography. You don't have to worry a whole lot about this. There's not going to be a ton of questions over it, but we still need to know it, and there's probably going to be at least one question about it on quizzes and tests. So make sure you know it. And it's a separation of a mixture by the difference in polarity. And mainly, chromatography has to deal with separating inks. When you think about it, the black ink in this black ballpoint pen isn't made from just some random plant that perfectly produces black ink. No, this is a chemical process where you put multiple chemicals and colored powders and stuff together to create this perfect number 7 black ink, or whatever you want to call it. That being said, it's a mixture. So we can separate those inks by their difference in polarity, and you end up having strips like this, where you put some kind of like liquid or solution on the strip, and then you put a drop of your ink, or you like put a little bit of that paper into ink, and that ink that you expose the solution on the paper to will, I think you understand the term, bleed. It'll bleed. It'll kind of, and it'll show the whole color palette that's inside of this ink and separate all the ink by the difference in polarity. Okay, now, since we've talked about physical separation methods, now let's talk about measuring with precision and accuracy. Now, we need to know the difference between precision and accuracy. Okay, so this pencil starts at 0 and ends a little bit more than halfway through 1, but it didn't get to 2. So if we look at that, it's 1.1, 2, 3, 4, 5, 6, 7, 8. I'm going to say it's right there. 1.8, not quite 1.9. So that's what? 1.85. I'll say this is centimeters. 1.85 centimeters. Okay, so it's about right there, which means we're at about 1.85 centimeters. Okay, the 8 is very accurate. The 5 is kind of a guesstimation because we just don't know. Okay, let's record the mass. We know we got 500 there, so it's going to start with 500. We got 40, 542.123.4, and the unit is grams. Just making sure that we know how to read a scale. Nothing's left into interpretation. It looks like that's right over the 0.4 section, so we don't have to guesstimate at all. Precision and accuracy. So, ask yourself this question: which one of these two rulers is more accurate? Yeah, it's the one that has more little tally marks here. Okay, that helps you be more accurate. If you're putting something right here that could look like it's 2.4 or 2.5. Like, hey, I don't know exactly. But when you're given more accurate readings on a measurement device or utensil or piece of lab equipment, you can more accurately tell where this thing is. And you can also go to more decimal places. Right here, we can only be accurate up to that decimal place kind of ish. We have to estimate. Here we know that it's at least 2.5, and then we have to guesstimate with that. On this side, we're guessing that one, okay, because we can be accurate that it's between here, but we can't be accurate in this area. We can be accurate here, but we have to guesstimate here. Sig figs, significant figures. You're going to hear it called sig figs more than likely by all the chemistry teachers. Okay, includes all digits for which the measuring instrument has markings. That's what I was talking about here. It has all these markings. This one doesn't have markings. So this will have more sig figs than this. Okay. So it includes all digits for which the measuring instrument has markings plus one which is estimated. So this had between 2 and 3. So this is accurate, and then we have one more, which is not. We're accurate here, and then we have one more, which is a estimation. It's an estimation. Okay, there's uncertainty in the last one. Okay, precision of measuring. A reasonable estimation of the final uncalibrated digit should be made. What do you think the length of the nail is? The length of the nail is? What do you think? I think the nail is probably right at 6.1 to 6.35. I think 6.35 is accurate. I think that's a good estimation. Let's go back into the screen. Because we know it's going to be at least 6. We know it's at least 3, but we have to guess here. And because it kind of looks like it's in the middle, we'll put 5. And I believe this is centimeters, because it's bigger right here. Okay. Square the length of the pencil. Looks like it ends right there. So it's at least 1. We're going to be accurate with that. And there goes 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. 1.85. That one's an estimation. And don't forget your units. Centimeters. $542.123. That looks, these are all accurate. There's no guesstimation here. That's right on top of 0.4 right there. Accuracy versus precision. I like teaching this. Not that I don't like teaching the other stuff, but I like this one in particular. Okay, accuracy is how close are you to the right answer? Just, are you right or wrong? Did you get what the correct answer is? Did you get close to what the value should be? Precision, on the other hand, is getting the same result over and over again. Could be completely right, could be completely wrong, but you're consistently getting the same thing. Okay, so precision. Okay, high precision means that you can repeat the same process and get the same answer. So when you look at it, all your data, like you can see in the chart below the table, is going to all look extremely similar. Okay? But accuracy, okay, is getting the right answer. Okay? Accuracy is getting the most. So let's look at this. Between student A, student B, and student C, who is the most accurate if sucrose's melting point should be 185 degrees Celsius? Yes. Student A, yeah, really close to 185, really close to 185, close to 185, a little off, but compared to the other two, I mean, answer is right around 185. Most precise though, look at the difference, okay? The difference in those is 0.1. Difference in those is over 1, and that's like over 2. This one's kind of far off. Look at how close those numbers are though. Student C is definitely the most precise. Even though it's not close to 185 degrees Celsius in any of the answers, all his answers, or her answers, student C's answers are all very similar, and each trial is having almost the identical answer or test completed. Least accurate. I'm looking at it. I would say student B is the least accurate, because go from 187.1 to 183 and then back up to 190. They're just kind of all over the place. Okay. Least precise. Oh, sorry. Least precise is B, and then least accurate. Come on, let's figure this out. Yeah, got it. Okay, and then student C would be the least accurate. Sorry for the confusion there. Okay, how accurate is student A? Let's do percent error. Okay, the accepted value is 185. Okay, that's the actual melting point of sucrose. And here's what they got, 184.7. Okay, so the difference in those numbers is 0.3. Let's calculate the error. So, if we do it, the error value was 0.3. The accepted value is 185. And then we're going to multiply that by 100. Go ahead and type that into your calculators really quick. I don't have a calculator in front of me, so I'm going to pull up my calculator app on my phone. 0.3 divided by 185 gives you that number, 0.00162162. If I multiply that by 100, the error is 0.16%. Okay, so why should we care about error? Well, we want to make sure that our experiments are relevant. We want to make sure that what we're doing matters. If, let's say, we're in the real world and you're running an experiment on something that's, could potentially be worth millions of dollars. So like, let's say it's a vaccine for COVID. You got to make sure that your error is very low, so that you can help save lives and make a legitimate impact on society. So in the laboratory, the final measured value is compared to an acceptable value, or otherwise known value, in order to evaluate the relevance of your experimental results. There's a lot of money in the hey, can you make this super accurate and worthwhile to me industry. Lots of medical research, research on vaccinations. Engineering is like huge on error. If you're off by like millimeters, they don't call it error in engineering, they call it like tolerance. Like How off are you from what's acceptable? Whenever you're building homes, you have to make sure your foundation is level. If it's off by a little bit, they say, that's off by, a certain tolerance or a certain percent error or something like that, and you have to stay within a certain means. So error is something that, most of y'all, if y'all get into some kind of STEM field, you're going to have to deal with. Okay, so what's more significant here? A 1 millimeter error, well, right for me, there we go. 1 millimeter error in a skateboard wheel diameter. Okay, so let's say this. Here's your skateboard wheel. I'm going to put like a little thing there. Or a 1 millimeter error in a truck wheel diameter. Okay, there's your truck wheel. Oh, look how perfectly circular that is. Okay, and there's look at that rim. That's cool. It's an awesome tire. If your tire looks like that, please go to a dealership or go to a mechanic and get it fixed. Okay, so which one of those is acceptable? Yeah, it's obvious. Okay, the truck tire. Okay, 1 millimeter is nothing. But a skateboard wheel, because it's so much smaller, that 1 millimeter is huge. Okay, that 1 millimeter may be the difference between that thing riding well and being lumpy, or having a difference in how the leveling of the skateboard is. It may to one side and make it to where it's just constantly going in circles. I don't know if you've ever been on a skateboard, but if you put pressure on one side, or if one wheel is messed up, you just kind of end up going in circles. And that's it. Have a wonderful day. Please reach out to your chemistry teacher if you have questions. The best way to engage with us is through Remind, Schoology messaging, or through email. Have a wonderful day.